In this video, we're going to work example problems involving acid-base reactions in aqueous solution. So remember, you don't want to confuse something like an oxidation-reduction reaction that occurs in aqueous solution that happens to involve an acid with what we're calling in this chapter an acid-base reaction. So in this chapter, the main reactions in aqueous solution that we're studying are precipitation reactions, acid-base reactions, and oxidation-reduction reactions. And the acid-base reactions we're referring to are acid-base neutralization reactions, in which case protons are transferred. No electrons are transferred, right? With a precipitation reaction, there's no transfer of protons or electrons. It's just a mixing up and interaction of different ions in solution. An acid-base reaction, the acid-base neutralization reaction, involves a transfer of protons, and redox reactions involve a transfer of electrons. But you could have a redox reaction in aqueous solution so if you've got solid zinc in a water environment, but it doesn't dissolve, and the dissolved in the water is hydrochloric acid, then what results is you have zinc chloride, aqueous, and then H2 gas comes out of the solution. Okay, but this is not what we're calling in this chapter an acid-base reaction. This is a redox reaction. It's a redox reaction that just happens to involve an acid. Okay, so just keep that in mind. Okay. Give Arrhenius's and Bronsted definitions of an acid and a base. Why are Bronsted definitions more useful in describing acid-base properties? So according to the Arrhenius definition, an acid is a substance that releases hydrogen ions in water, H+ ions, while a base is a substance that releases hydroxide ions, OH- ions in water. Okay, that's the Arrhenius definition. The Bronsted definition is that so an acid is defined to be a proton donor and a base is defined to be a proton acceptor. Okay, now the Bronsted definitions are more useful because they aren't restricted to aqueous solutions. So according to the Bronsted definitions, if you have any substance to where if that substance is added to a system, no matter what the system is, and as a result, the proton or H+ ion concentration of that system increases, then that substance is considered to be an acid or acidic, right? And then similarly, according to the Bronsted definition for a base, if you have any substance to where if that substance is added to a system, no matter what the system is, and as a result, the proton concentration decreases, then that substance is considered to be a base or basic. Okay, but now the Bronsted definition of acids and bases also increases the versatility of the Arrhenius definition with respect to aqueous solutions as well, because Arrhenius says that a base is a substance that yields OH- ions when added to aqueous solution, right? But Bronsted says that a base with respect to aqueous solution would be any substance that accepts protons when added to the solution. So another way of looking at this is that when the substance is added to the solution, the H+ concentration decreases. Okay, but if you noticed, the Bronsted definition for a base in aqueous solution isn't saying that the substance must yield OH- ions. And this is important because the yielding of OH- ions in water isn't the one and only direct way for a substance to act as a base in aqueous solution. For example, if you think about an oxide ionic compound that's soluble in water, so the anion is O2-, like sodium oxide, potassium oxide, calcium oxide. Well, we know an ionic compound that's soluble in water is a strong electrolyte. So being an oxide, these compounds break up into ions, with one of the ions being an O2- ion, right? Well, an O2- ion in aqueous solution is going to end up accepting H plus ions, right? It's going to first accept an H plus ion to become OH minus. So yes, it did eventually yield OH minus ions, but not directly. The like an oxide, an ionic compound that's an oxide, is really fundamentally yielding the O2 minus ions, not OH minus ions. So you can see how the Bronsted definition is ensuring that substances like soluble oxides are still properly classified as basic. Give an example of a monoprotic acid, a diprotic acid, and a triprotic acid. Okay, a monoprotic acid is an acid to where each unit of the acid yields only one hydrogen ion once it's dissolved or ionized in water. Okay, like HCl, hydrochloric acid, for example. When this is dissolved in water, it breaks up into dissolved, hydrated H plus cations and Cl minus anions. And that's it. This doesn't have any more protons that it can break off with. Each unit of HCl is going to result in one proton. So this is considered monoprotic, a monoprotic acid. Okay, a diprotic acid is going to, in the end up yielding two protons into the solution. So sulfuric acid, for example, you've got H2SO4 aqueous. This breaks up into H plus ions, and you've got HSO4 minus ions. Okay. However, this is also in its own right an acid, HSO4 minus. So you can think about like you start with pure water, add in some sulfuric acid, it breaks up into H plus and HO4 minus, dissolved H plus and HSO4 minus ions. But then even in this environment, it's still energetically favorable, chemically favorable for this to go ahead and dissolve further. So now this dissociation process is reversible. So this is acting as a weak acid, but it still does dissociate. Okay, but still though, because this initial acid here, upon being added to the water, overall what results is for each one of these you have two protons in the solution. That's why this is considered diprotic. Okay, and so now a triprotic acid is just going to be yielding three protons upon dissolving in water. So phosphoric acid. Okay, now the initial dissociation process is reversible. So here, this is a strong acid because it breaks up completely, and then the resulting secondary acid is a weak acid. With phosphoric acid, this is a weak acid initially, but as far as the definition of the monoprotic, diprotic, or triprotic definition, whether or not the initial acid is weak, strong, all of that doesn't matter. It's just saying that, so, okay, and this initially is going to break up into H plus ions, and then okay, but now even in this environment with H plus ions, it's still chemically favorable for this to go ahead and dissociate as well. And this is going to be reversible. Okay, but now even in this environment here, so we already have an acidic environment with H plus ions, but it's still chemically favorable for this to go ahead and break up to some extent. So this is going to act as an acid as well, a weak acid. Okay, but still, though, upon dissolving, just for every 1 unit of this acid that's dissolved, the net result is 3 dissolved protons in the solution. So this is considered triprotic, a triprotic acid. What are the characteristics of an acid-base neutralization reaction? Okay, so an acid-base neutralization reaction is a reaction between an acid and a base in solution, in aqueous solution. This definition could apply to any system, not just an aqueous solution, but let's think about aqueous solution. So you've got an aqueous solution with an acid dissolved, and then another aqueous solution with a base dissolved. And then if you combine these solutions, what results is an acid-base neutralization reaction. Okay, so the characteristics of an acid-base neutralization reaction are that, so one of the results is that you're going to have H plus ions interacting with OH minus ions, and they're going to chemically combine to form water, H2O liquid. So after a neutralization reaction takes place, you end up with more overall water than what you initially started with. Okay, now additionally, in the solution, you have a dissolved anion that was initially associated with the acid, and a dissolved cation that was initially associated with the base. And these two ions interact to form an ionic compound. So this ionic compound could just be aqueous, meaning everything just stays dissolved, but you still kind of look at it as an ionic compound. Or perhaps it precipitates out as a solid, but this resulting ionic compound is called a salt. So with an acid-base neutralization reaction, the main characteristics are that you've got an acid and a base mixed together, these two aqueous solutions mixed together, and what results is a salt and water. All right, now, what factors qualify a compound as a salt? And then specify which of the following compounds are salts. Okay, so the textbook tells us that a salt is an ionic compound. Okay, that's the first characteristic, an ionic compound. Okay, but then it's an ionic compound to where, as any ionic compound, that to where the cation is not H plus, and the anion is not OH minus or O2 minus. Then you have a salt. A salt is any ionic compound to where the cation is not H plus, as well as the anion is not OH minus or O2 minus. This is like an and criteria. Neither one of these can be true for you to have a salt. So based on what we just discussed as one of the main characteristics of an acid-base neutralization reaction being that a salt is produced, how does this make sense from the perspective of this definition of a salt? Well, okay, a salt can't be an ionic compound that contains H plus cations, because in a neutralization reaction, H plus ions are interacting with OH minus ions to form water, right? So how could you have a salt that's formed in a neutralization reaction involving H plus cations? And it's the same idea with OH minus or O2 minus anions. In a neutralization reaction, the OH minus or the O2 minus ions are directly involved with the the combination with the H plus cations to form water. Okay, but in general, any other cations other than H plus or anions other than OH minus or O2 minus could be associated with the cation anion ionic compound interaction in a neutralization reaction. And so that's where this definition of a salt comes from. Okay, so is CH4 a salt? Well, no. First of all, this isn't an ionic compound. Like, yes, this does contain hydrogens, but that doesn't really matter when you consider that this isn't an ionic compound. So even if this was some molecule that didn't contain hydrogens, just some combination of carbon with other elements other than hydrogen, it still wouldn't matter. Why not? Well, because it's the reason why a salt has to be an ionic compound is, so think about the whole neutralization process. You start with these acids and bases dissolved in solution, which all acids and bases are electrolytes. You've got these ions in solution. The salt is going to be the interaction between ions. It's going to be this ionic compound, right? Even if it doesn't precipitate out of the solution as a result of the neutralization reaction, we still look at it as an ionic compound, right? We could, in the molecular equation, we'll write it as, whatever the ionic compound is, aqueous. Okay, so no, this is not a salt. Sodium fluoride, that's an ionic compound that doesn't involve H plus, OH minus, or O2 minus ions, so this is a salt. Okay, this is an ionic compound, but you've got OH minus anions, so no. Here, ionic compound with O2 minus anions, no. Here, you have an ionic compound that's a bond between Ba2 plus and SO42 minus ions, so yes. Here, well, this isn't even an ionic compound, right? So we could just, from there, we could deduce that this isn't a salt. Okay, NH3, well, okay, this is a weak base, right? So no, this can't be a salt. Potassium bromide, that's an ionic compound where potassium is the cation and bromide is the anion. So yes, that's a salt. Identify the following as a weak or strong acid or a weak or strong base. Okay, so we can reference the table that the textbook gives regarding strong and weak acids, but we actually aren't given a table, a dedicated table regarding strong and weak bases. But it's also helpful to think about the meaning of a strong acid, strong base, and weak acid, weak base. So remember, this strong, weak designation for acids and bases is just referring to if the acid or base is a strong or weak electrolyte. Okay, so with that in mind, let's think about NH3 ammonia. Okay, so NH3, we talked about how when dissolved in water, NH3 becomes NH4 plus. So it's a proton acceptor and therefore a base. But this reaction is reversible, so it's a weak base. So this is a weak base, right? So we can, this was a little bit confusing. The whole dissolving process of NH3 was different than a typical acid or base dissolving that we saw. So you could write this in one of two ways. You could say, so NH3 aqueous plus H plus aqueous results in, and this is reversible, so it's a weak process, NH4 plus aqueous. Okay, but the only issue with this is it sort of implies that, well, only if you dissolve NH3 in an acidic environment, that's when it only acts as a proton acceptor. But no, it's got the NH3 ammonia has that official designation as a base, because if you dissolved NH3 in neutral water, like pure water, it still forms NH4 plus. So it can be more useful to write this dissolving process this way. So you've got NH3 aqueous plus H2O liquid results in You see, this is a little more realistic as far as what's happening. You've really got like neutral water, NH3 gets dissolved, and it's pulling hydrogens off of water, resulting in NH4 plus and yielding these OH minus ions. It's producing a basic solution. Okay, but again, this is a weak process. All right, H3PO4, that's phosphoric acid. And we can see phosphoric acid is a weak acid. And we saw that phosphoric acid is triprotic, right? But we're really referring to this first dissociation process here. It was a weak dissociation, right? This phosphoric, because these are technically distinct species. This is its own acid. This is its own acid. Yes, this is triprotic because at the end of the day, after dissolving, you're going to have 3 protons result. But from a classification standpoint, this is its own distinct acid, and it dissociates reversibly, so it's weak. Okay, lithium hydroxide. So with an OH group here, we're thinking about how this is some form of a base, but we weren't explicitly given any dedicated table regarding strong and weak bases, but we can think about how, so we know that all ionic compounds are strong electrolytes. So the question is then, is lithium hydroxide soluble in water or not? If it's not, well then it can't be any kind of a base because it's not going to yield any OH minus ions in solution, right? But if it is soluble, well then it's going to be a strong base. So if we come to the solubility rules for ionic compounds, we've got all hydroxides are insoluble, with the soluble exceptions involving Ba2 plus and any alkali metal. So lithium is an alkali metal. So this is a strong base. Okay, HCOOH, formic acid. They don't list formic acid in this table. Acetic acid looks similar, but it's not the same. Okay, so you can do a Google search on this, do a little research on this, on formic acid. The structure of formic acid is okay, and after doing some research, you'll find that formic acid is a monoprotic weak acid. And this, from the structure, this makes sense. It's going to be monoprotic. It'll give up this hydrogen, but then this hydrogen's not going to be dissociated, right? But the giving up of this hydrogen is a reversible reaction, so it's a weak acid. Okay, H2SO4, sulfuric acid. We can see here in the table, sulfuric acid is a strong acid, but we saw that sulfuric acid is diprotic, right? But now the second dissociation is a weak process, but that's referring to how this is a weak acid. But the H2SO4 itself is a strong acid. Okay, HF, hydrofluoric acid, is a weak acid. All right, barium hydroxide is, we can see here, it's listed as a strong electrolyte, and it's an ionic compound. It's also soluble. Hydroxides are insoluble, with Ba2 plus cation being one exception. So this is a strong base. Identify each of the following species as a Bronsted acid, base, or both. Okay, so we're starting off with PO4 3-. We can come to this breakdown of phosphoric acid, which, so if you dissolved phosphoric acid, let's think about it like in neutral water, and once everything got mixed up and was at equilibrium, one of the species floating around dissolved would be this PO4 3-. Okay, and so what can we, as far as the acidic or basic classifications, how can we classify this substance here? Well, in the solution, it's going to be, to some extent, it's going to be, since this is reversible, it's going to be combining with H plus ions. It's going to be accepting H plus ions, right? So this is going to be acting as a Bronsted base. But now, as far as acting as an acid, well, no, this can't donate any protons to the solution. So a base. Okay, ClO2 minus, we can think about how, so HClO2, if you do a Google search on this, this is chlorous acid, and it's a weak acid. So it will dissociate reversibly in water into H plus and okay, now there's the species we're being asked about. So, okay, since this is a reversible reaction, well, in aqueous solution, this is going to act as a proton acceptor, right? So this is we can say this is a base, Bronsted base. Okay, NH4 plus, well, we know where this comes from when you dissolve ammonia in water. So let's do this. This is a reversible reaction. Okay, so here's the species we're being asked about. So in water, this is going to yield H plus ions to some extent. So this is an acid. This acts as an acid. Okay, now HCO3 minus, we can think about carbonic acid. So H2CO3 is a weak acid, so it's going to dissociate like shown. Okay, but now this is a diprotic acid, which means that this is also an acid in this environment here. So you have a second step where you have this is going to be weak. Okay, and so what's interesting here is that because, this definitely acts as an acid, but it also acts at the same time as a base because this is reversible. So it can go in this direction and accept a proton. So this is acid and base. And we can compare this to what we looked at as with sulfuric acid. So this HSO4, yeah, this is a diprotic scenario as well, but this is not going to act also as a base. This is only going to act as an acid. Why? Well, because this is not reversible here. This is not going to go in the other direction. You see? Okay. Balance the following equations and write the corresponding ionic and net ionic equations, if appropriate. So we've got these mixing of these acid and base solutions. So a neutralization process is going to take place. And so for these neutralization reactions, we want to write the molecular equation, the ionic equation, and the net ionic equation, similar to what we did with precipitation reactions. Okay, but now what's different when it comes to neutralization reactions, what's different from precipitation reactions is, so with precipitation reactions, we were only dealing with, at least for the precipitation reactions we studied in this chapter, we were only dealing with ionic compounds, which made it simple from the perspective that ionic compounds are either going to be soluble in strong electrolytes or they're going to be insoluble. But now when it comes to these with acid-base neutralization reactions, we have the added variable of we could be dealing with a weak acid or a weak base, right? So how do we work with weak acids or weak bases in regards to ionic and net ionic equations? Well, okay, we're going to start off with the molecular equation. We're not thinking about breaking up anything into ions no matter what. So the whole weak acid, weak base idea doesn't come into play with the molecular equation, okay, because we're starting off with, we've got acetic acid and potassium hydroxide. Both are aqueous. They're both dissolved. Okay, but even though acetic acid is a weak acid, and this is an ionic compound, and it's obviously soluble. They put aqueous, so this is going to be a strong base. We still just, for the molecular equation, we just write out. We don't dissociate anything, no matter what. Okay, but now, since we've got this reaction in aqueous solution here between an acid and a base, well, then we just use our knowledge of, we know this is a neutralization reaction. We know that we're going to end up with, for any neutralization reaction in aqueous solution, we're going to end up with a salt and water. Okay, so what's the salt going to be? Well, we just combine the cation associated with the base and the anion associated with the acid. So you've got K plus and CH3COO minus. Okay, so that's KCH3COO. Now, but we do want to check, do we put aqueous here or solid here, right, for this ionic compound? So here's the solubility rules for ionic compounds, some common ionic compounds. So any ionic compound that has potassium as a cation is going to be soluble with no exceptions. Okay, so we just put this as aqueous. All right, and then for any, we know this is a neutralization reaction, right? This is an aqueous reaction here between acid and base. So we're going to have the salt and we're going to have water. Okay, but we're not done. We need to balance this, right? So, okay, we've got one CH3COO on the left and right. We have one potassium on the left and right. And we've got, let's see. Okay, so I can't really group the CH3COOs together like that because, or maybe I can. So let's see. A is, so you've got AH plus KOH, KA. Okay, so the A's are balanced, the K's are balanced, the O's are balanced, and the H's are balanced. Okay, so this is already balanced. So there's the molecular equation. All right. Now, for the ionic equation, when it comes to dealing with weak electrolytes, weak acids or weak bases, all we do is we don't break up anything that's a weak electrolyte into ions in the ionic or net ionic equation. That's it. That's the only difference. So, okay, we know this is a weak acid here, so we just leave it as it is in the ionic equation. Okay, but now this is a strong base, so we break it up. Okay, now this is a soluble ionic compound, right? So we break it up. It's a strong electrolyte. Okay, there's the ionic equation. Now we cancel spectator ions, and what's left is the net ionic equation. So and there we go. Okay, part B. We've got H2CO3 aqueous, which is carbonic acid. We talked about carbonic acid a second ago. This is a diprotic weak acid. Okay, but now just to keep things simple, we're just going to consider the initial carbonic acid and its full dissociation into H plus and CO3 2 minus ions. Okay, so we've got carbonic acid aqueous, sodium hydroxide aqueous. Okay, so again, this is a reaction in aqueous solution between an acid and a base. That means it's a neutralization reaction. So in all circumstances, the result is going to be water. The products are going to be water and a salt. So the salt in this case, we're going to think about, so CO3 2 minus is the anion carbonate, and that's going to be interacting with the Na plus cation. So Na2CO3. And okay, is this soluble or insoluble, this ionic compound? All ionic compounds that contain sodium as a cation are soluble. So we put aqueous. Okay, now let's balance this. We've got 2 sodiums on the left, 2 on the right, a carbonate on the left, a carbonate on the right, 4 hydrogens on the left, 4 on the right, 4 hydrogens on the left. Now we got 4 on the right, 5 oxygens on the left, 5 on the right. So, okay, that's balanced. There's the molecular equation. Now the ionic equation. So, okay, this is a weak acid, so we leave this as a compound. Okay, this is a soluble ionic compound, so it's it's a strong electrolyte. So you've got 2 Na plus and okay, this is an ionic compound. That's aqueous. Okay, there's the ionic equation. Now, the net ionic equation, let's cancel the spectator ions. And so we get okay. And there's the net ionic equation. Okay, part C, we've got HNO3. That's nitric acid. It's a strong acid. And then we've got barium hydroxide, which we talked about earlier. That's a strong base. So we have a neutralization reaction between a strong acid and a strong base. What's going to be what would you guess would be the net ionic equation in this case for a neutralization reaction between a strong acid and a strong base? Okay, so we've got, with the molecular equation, HNO3 aqueous. All right, now what's the salt? That's barium, Ba2 plus, nitrate, NO3 minus. So BaNO3 2. Now, is this aqueous or solid? So nitrates are all soluble with no exceptions. So aqueous and water. Remember, any neutralization reaction, if you're thinking about a reaction in aqueous solution between an acid and a base, is always going to, the products are going to be a salt and water, with the salt being the combination of the cation associated with the base and the anion associated with the acid. Okay, now the ionic equation. Everything is strong, a strong electrolyte here, so you've got, let's see. Oh no, we need to balance this. Make sure it's balanced. So 1 barium on the left, 1 barium on the right. You need 2 here to balance the nitrates. And let's see. So now we've got 6. We have 8 oxygens. So what if we put a 2 here? So the bariums are balanced. The nitrates are balanced. And now you You have 4 hydrogens on the left, 4 on the right, and then 8 oxygens on the left, 8 on the right. So yeah, that's balanced. Okay, so now the ionic equation we've got, so 2H plus 2NO3 minus, then Ba2 plus, and then 2OH minus. Okay, now Ba2 plus, and then 2NO3 minus, and then 2H2O. Okay, there's the ionic equation. Now let's cancel the spectator ions, and we're left with the net ionic equation, which is, so you have 2H plus 2OH minus gives 2H2O, but we can, the 2 is redundant, so we can just write this as and there's the net ionic equation. Okay, let's go through the same process for these 3 equations. Part A, we've got hydrobromic acid, which is a strong acid, and then we've got ammonia, which we know is a weak base. Okay, but because ammonia is unconventional in the way that it dissolves in water, as we know, to yield OH minus ions and act as a base, this is a little bit tricky. This is tricky from the standpoint of how exactly we're going to represent the chemical equations here, the molecular, ionic, and net ionic equations for this neutralization reaction that involves ammonia as the base. Because, okay, we talked about earlier how there's 2 ways you can think about the process of ammonia dissolving in water. Right, here's one and here's another. There's potentially more ways to think about this if you want to incorporate the hydronium H3O plus ion instead. But just thinking about H plus, there's 2 ways to represent this, the dissolving of ammonia in water. And really, if you're thinking about ammonia acting as the true pure base that it is, then this second equation is most appropriate. Because, as I had mentioned previously, this first equation is more of painting a picture of ammonia being added to an already acidic solution, right? There's H plus ions floating around. You add ammonia, and this is what results. Okay, but I mean, it's not like this is wrong. This first equation is wrong. Absolutely not. So what I mean by how this second equation is showing ammonia's character as a pure base is that you could think about how potentially you could have a very highly acidic solution with a high concentration of H plus ions, okay? Well, there might be some substance that when added to the acidic solution in this circumstance would absorb some of the H plus ions because there's such a high concentration and therefore act as a base. But if you added that same substance to pure water, where there was not this big imbalance of H plus ions, maybe the result wouldn't necessarily be OH minus ions in solution, which means that the solution is becoming more basic, right? Because like the OH minus ions present, it means that you have a compound that will pull H plus ions out of the solution when it interacts with them. Okay, but maybe this substance that does technically act as a base in a highly acidic, high concentration of H plus ions solution doesn't technically act as a base in a neutral water solution. So in that case, you wouldn't look at that substance as a true pure base, right? And so that's what this equation is illustrating about ammonia. It's not like it only when it interacts with rogue H plus ions in water does it pull in those protons. No, you could have neutral water with, in effect, no H plus ions in the solution, but it's still going to pull an H plus off of the water molecules. Okay, and so which of these representations then do we want to use to write out the ionic and net ionic equations and the molecular equation for this first reaction here, this neutralization reaction? Well, to be honest with you, it's really personal preference. Neither way is incorrect. Whichever way you feel is the clearest for how you're trying to present this chemical reaction to yourself or to someone else is the best way. Because we could make arguments that both ways are the best representation of this reaction. Because, okay, from one perspective, this is a neutralization reaction, right? That's exactly what it is. You have H plus ions being added into the solution by the hydrobromic acid, and those H plus ions are being absorbed by the dissolved NH3, ammonia. Well, okay, in that case, this is the correct perspective to use for the ammonia, right? It's exactly what this is showing. You have a aqueous ammonia interacting with aqueous H plus ions to produce NH4 plus ions. This is the whole neutralization process right here. Okay, but from another perspective, it's like we're starting with two separate beakers, one of hydrobromic acid and one of aqueous ammonia base, a basic solution of aqueous ammonia, and then from there we're mixing those two solutions together. Okay, so let's go ahead and go through both perspectives and see the result. What you're actually going to see is using the perspective of ammonia with this perspective here is actually going to do a better job of painting the picture, at least in my opinion, of this neutralization reaction. So, okay, but let's go through this perspective first. All right, so it's going to be a little bit easier if we do the ionic equation first and then come back to the molecular equation. So, okay, HBr is a strong acid, so we're going to put it in the ionic equation as it's disassociated. Okay. Now, what do we do with NH3 here? Okay, because this is confusing in that this doesn't dissociate, right? Well, okay, to figure this out, let's go back and think about the overarching purpose of the ionic and net ionic equations. What's the whole reason for these equations? Why are they used? Well, they're just used to create a more illustrative picture of the reaction that's taking place in the aqueous solution. In particular, they're painting a picture of the ions or the particles floating around in the solution interacting, right? And so, okay, in that sense then, remember how we think about the reactant side of these reactions in aqueous solution as sort of like the instantaneous moment right when the solutions are mixed, before the particles have interacted and any chemical reactions have taken place. What's the state at the instant they're mixed? What are the particles floating around? Okay, we've got the H plus and the Br minuses floating around, and then we've just got the NH3s floating around, right? The ammonia doesn't dissociate. It dissolves in the same way that like a sugar molecule dissolves. Just the whole molecule gets hydrated. So you do have these NH3 particles just dissolved floating around. So we're just going to put NH3 then. Okay, so that's the state, as far as the ionic equation, all of the particles floating around, that's the state before any of the particles interact. Right after everything's mixed, but before interactions have taken place. Okay, so now in the products, we think about, okay, once everything interacts, what happens? What chemical reactions take place? Or like does something precipitate out, etc. Well, okay, if we look here, we've got when the H plus interacts with NH3, we know what's going to result is ammonium. Right? But like it's not dissociated or anything. This is the ionic equation. It's a full dissolved NH4 plus ion. Okay, but then the Br minus doesn't do anything. Right? It's a spectator ion. So here's the ionic equation. Now we cancel the spectator ions, and what's left is the net ionic equation. And actually, let's go ahead and think about balancing, making sure this is balanced. 4 hydrogens on the left, 4 on the right, nitrogen on the left, nitrogen on the right, bromine on the left, bromine on the right. Okay, so here's the ionic equation, and here's the net ionic equation. Now, we can come back to the molecular equation, okay? And so to figure out what this is supposed to be, let's remind ourselves of the overarching purpose of the molecular equation, in that it's more of illustrating how the reaction was carried out, how it took place, what substances were involved. So like in a lab, what solutions did you combine, right? Well, okay, it was a hydrobromic acid solution, aqueous solution, mixed with an ammonium aqueous solution, right? Okay. And what resulted is these NH4 plus and Br minus ions in the solution. But we're in the molecular equation, we're not going to show this as dissociated. We're going to show this as an aqueous ionic compound. So let's do okay, so there's the molecular equation. Okay, but the problem with this is that, in my opinion, so you'll see some solutions that would go through a problem like this way, but in my opinion, the issue with this is that, so it doesn't show you that this is definitely a neutralization reaction. So, okay, what's the definitive salt, and where's the water being produced, right? Any neutralization reaction, you're going to generate water. You're going to end up with more pure water than what you initially started with in the 2 beakers. So where's the water here, right? Where's the, you'd like to see the starting solutions, then the salt and the water. Okay, so let's do the other perspective. This isn't wrong, but I think you'll agree that the other perspective is more illustrative of the chemical reaction taking place here in this neutralization reaction, the whole chemical process, which is the point of all this. That's the point of these equations. Okay, so once again, let's to make this easier, let's start with the ionic equation. So we've got H plus aqueous, hydrobromic acid is a strong acid. Okay, now for NH3, we're going to think about how when we bring in the NH3, the ammonia beaker, what's present in the solution is, so okay, the NH3 and the H2O interact, and the result is these ions in the solution. Okay, but like for simplicity, like we did with the diprotic acid earlier, we're just going to assume a full dissociation here. So we're just going to write in the ionic equation, these 2 ions. So we've got NH4 plus aqueous and OH minus aqueous. Okay. So here's the state right when the solutions are mixed, the instant they're mixed, before any ions have had a chance to interact. So now let's mix and match everything and write out what results. So, okay, first of all, we can see we've got H plus ions and OH minus ions. Great. So that's going to result in liquid water, right? So we've shown the generation of water for sure. And now, so what else is left? Well, we've got the Br minus and the NH4 plus ions are going to interact, and that's going to be the salt. And yeah, okay, we want to check, make sure this salt is see if it's soluble or insoluble. I'm not sure if I did that when we did the first perspective. So ammonium, all ionic compounds that involve the ammonium cation are soluble with no exceptions, okay? And there we go. There's the ionic equation. And this is also going to be the net ionic equation because there's no spectator ions. Okay, and so now let's do the molecular equation. So we've got HBr aqueous. Okay, now how we're going to represent the NH3 in this case, well, we're going to use this sort of alternate representation, the NH4OH, but this is the molecular equation, so we write this as a full compound. Okay, and what results is, well, okay, is this balanced? 4, 5, 6 hydrogens on the left, 6 on the right, a single oxygen on the left, single oxygen on the right, Br on the left, Br on the right. Yeah, it's balanced. Okay, so we've got okay, and there's the molecular equation. And so you can see how this is more illustrative, in my opinion, of the chemical reactions taking place in this neutralization reaction, because we can see the resulting salt, and then we can see the water being generated. But the only kind of downfall is the fact that we've got the ammonia represented by this ammonium hydroxide, which isn't, that's not the ideal for the molecular equation, right? The molecular equation, you're trying to show, no, we mixed hydrobromic acid and aqueous ammonia solutions. We purchased ammonia and mixed it in with water. We didn't purchase like ammonia, some sort of like ammonium hydroxide substance. Okay, part B. So we've got barium hydroxide. They put the base first here, and phosphoric acid. So we know that this is going to be a triprotic weak acid. And again, just for simplicity, we're only going to consider the fully ionized acid for the case of like a diprotic or triprotic acid as far as the resulting salt and the resulting molecular equation. Then we've got barium hydroxide, which is a strong base. So, okay, let's go ahead and just put the acid first. Okay, the salt is going to be, you have Ba2 plus interacting with PO4 3 minus. So barium phosphate is an ionic compound that is, phosphates are insoluble except when bonded with the ammonium ion or an alkali metal. Barium is an alkaline earth metal, so this is actually this is going to be insoluble for this neutralization reaction. So this is actually going to precipitate out. This salt is going to precipitate out. Okay, so there's the salt and water. Now let's balance this. So 3 bariums on the right, 3 on the left. You got 1 phosphate on the left, 2 on the right. So now the phosphates are balanced. Let's see, 6 plus 6, so 12 hydrogens on the left, 12 on the right. So, okay, the bariums are balanced, the hydrogens are balanced, the phosphates are balanced. Now the oxygens, we've got 8 plus 6, 14, 8 plus 6, 14. So this is balanced. Okay, now the ionic equation, we've got, this is a weak acid, so we leave it with its full chemical formula. We've got a strong base here. So this is, let's see, it's going to be 6 OH minuses. Right? This is just going to fully dissociate into the ions. Then you've got okay, there's the ionic equation. Now, that's also the net ionic equation. There's no spectator ions. So the ionic and the net ionic equations are the same in this case. Okay, HClO4 is perchloric acid. It's a strong acid. And magnesium hydroxide is a, Okay, it's not even aqueous. So yeah, it's saying if appropriate. Well, this is not appropriate. Not appropriate for an ionic or net ionic equation. I mean, we could write the ionic equation here, but what I'm saying, it's not appropriate because there's no chemical reaction that's going to take place here. At least if we're just thinking about strictly like an acid-base neutralization reaction, right? Like you could look at this and say you've got hydroxides, that's a base, and that's going to be neutralized with the H pluses of these acids. Well, no, because this isn't going to yield any OH minus ions. Yeah, in the upcoming section, we're going to talk about that you can't have something that doesn't dissolve in solution in the water react chemically with ions in the solution. That could potentially happen, but right now in this video, thinking about acid-base neutralization reactions, there's not going to be any, we're not going to have any ions dissolved in this solution that are going to interact to precipitate out or chemically react, etc. Nothing's going to happen here. So there's no chemical reaction.